Let's see one more problem. The number of perfect matchings possible for k to n. Okay, we'll understand this problem with n value 2. When n value 2, it is k 2 2. That means 2 into 2, which will be k4. First, let me draw k4. 1 2 3 4. It's a complete graph. Then you will have like this: 1 2 3 4, 2 2 3, 1 2 4, everything, right? So in this graph, how many perfect matchings possible? So perfect matching is a matching where every vertex should be matched. Then you match 1 and 2 like this, then match 3 and 4 like this. This is one perfect matching for this graph. So why I have to map 1 to 2? Why not 1 with 3? Then you get 2 to 4, right? This is second perfect matching. I am listing out all possible matchings: 1 2, then 1 3. Now if I map 1 4, you get 2 to 3, isn't it? So this is the third. So in any matching, either one should be matched to 2 or 3 or 4, and I tried all possible things, right? I covered 1 2 case, 1 3 case, 1 4 case. So there is nothing else, right? That's why the number of perfect matchings are 3. Let's substitute n value 2, so that you should get 3 as the answer. So option A is wrong because 2 2 is a 4. 4 factorial is 24. Option A wrong. Option B, 4 factorial by 2 square, which is nothing but 24 by 4, 6. Wrong option. Then option C is 24 by, since 2 in factorial is 24, by 2 square 4 into 2 factorial 8. So 24 by 8 is 3. Maybe correct answer. Let's go to option D. It will be 24 by n factorial, 2 factorial. It is, which is nothing but 12, which is wrong option. So only C is matching. That's why this should be the correct answer. But let's generalize it. Why it should be correct? So why it is correct? Because I generalize it. I can do the perfect matchings like this. First of all, take all the vertices. Let's say 1, 2, 3 to n. In any perfect matching, let's say one should be matched to something, right? Then how many different ways one can be mapped? Since there are 2n minus 1 other vertices, since it's a complete graph, vertex 1 in matching can be mapped to any of those 2n minus 1 vertices. That's why. So 1 can be mapped in 2n minus 1 ways. Okay. Then the next vertex in this line, so I arrange them in the line first. If 1 gets 2n minus 1 options, now the next element, so why I'm saying next element, why I'm not saying 2, I will tell you. If 1 takes 2 as a partner, then we don't worry about 2, right? So that's why if 2 goes, no problem. Finally, there will be next element, right? I'm talking about next element. That next element, example 1 takes 2 and it goes out, like if 1 takes 2. Then 3 will have, the next number 3 will have how many options? 3 can take, because 3 cannot take 1 and 2, then 3 can take any of the 2n minus 3 elements. That's why 2n minus 3 ways 3 can be mapped. Okay. If 3 takes, let's say 5, okay, just possibility I'm talking about. Out of them, 3 might take 5, one of the example. Then the next number is what? 4, right? Then that 4 will have, because 1 2 gone, 3 5 gone, then with respect to 4 there are 2n minus 4 elements. Apart from 4 there are 2n minus 5 elements. Anything 4 can pick, then that 4 can be mapped to 2n minus 5 ways. Understand? In that way I can say that the first element in this list gets 2n minus 1 options. Second element in the list, whatever it may be, that will get 2n minus 3 options because 2 elements are gone. Then the next element gets 2n minus 5 options, so on. Finally, so if you continue this process, example there are 8 elements, 1 2 3 4 5 6 7 8. If 1 picks 3, 2 picks 4, 5 picks 7, then the last pair will have only one option. That is what I want to tell. If you do this process, then first, for the first element will have 7 options, second element will have 5 options, third element will have 3 options, fourth element will have only one option. Correct? That's why this series ends with 1. Okay, this is the answer, right? Example, there are only 2 candidates, like 4 elements, 1 2 3 4. How many ways you can map them? If one gets, how many ways one can be mapped? That's fine. For one, there are 3 options, right? 3 ways. Okay. Okay. Example 1 takes 2. Then the next element is 3, right? How many ways 3 can be mapped? Only one way, right? That is 3 to 4. That's why first element has 3 ways. Second element has one way. According to product rule, the total number of ways are nothing but 3 into 1, right? Here also same thing. First element has 2n minus 1 ways, second element has 2n minus 3 ways, so on. Some last element has one way, then the total number of ways equal to 2n minus 1 into 2n minus 3, so on up to 1. What I do is to get 2n factorial, so something is missing here. What is that? 2n is missing. I add it. 2n minus 1 I'll keep as it is into. So here 2n minus 2 is missing. Let me add it. Then next 2n minus 3, so on, 2n minus 4 up to 1. Okay. So when I do that, I should divide that with whatever the elements added, right? So 2n is added, 2n minus 2 is added, and 2n minus 4 is added in the series, right? So this is this idea. Let's simplify it here. So this will become 2n into 2n minus 1, 2n minus 2 up to 1 will be 2n factorial, whole factorial, by this 2n into 2n minus 2 into 2n minus 4. In that, if I take 2 common, 2 common here, 2 common here, I am taking, because since every number is even number, 2n is even number, 2n minus 2 is even number, so on. If I take 2 common in every way, then 2 into n, 2 into n minus 1, 2 into n minus 2, so on. The last one will be 2, right? Because all the even numbers you are writing in decreasing order, then the last number will be 2. Then that will become 2n whole factorial by, how many 2's will be there? In, see, for n 1 2, n minus 1 1 2, in that way 2 into 1. So 1 to n, there are n numbers, that's why there are n 2's. 2 into n times will be 2 power n into the remaining thing. You see, if I cancel 2's, because I have written 2 power n into n minus 1 n minus 2 up to 1, that is nothing but n factorial. That's why answer is 2n factorial by n factorial. So option C is the right choice. Okay.